Hi everyone, I'm Ashley Bemis, a postdoc in the Allegro group, and today I will be discussing how to image ALMA data using CASA. To begin imaging a project, you should have already run the script for PI. As we've already seen, the script for PI will call the ALMA science pipeline, which will apply calibrations to the visibilities of your dataset. Once you've run script for PI, you will have obtained a measurement set with those calibrated visibilities, data weights, and UV information for gridding. This measurement set will only contain data on your science target, which will have been split out of intermediate measurement sets that also contain calibrator data. An imaging pipeline was implemented in Cycle 4 and has been combined with the calibration pipeline. Projects that have been imaged with the pipeline are considered science-ready, but they will be limited to the main science goals of your project. So if you want to produce additional images or re-image yourself, you can do so manually through CASA, which is what this talk will focus on today. Before I move on to imaging, I'd like to highlight how the PI-delivered projects were calibrated and imaged in each cycle. This plot compares the number of pipeline-only calibrated and imaged datasets relative to the number of projects that were either semi-manually calibrated or pipeline-calibrated but manually imaged. The number of pipeline-processed images in delivered products significantly exceeds manually produced images starting in Cycle 5, and this continues to be the case. The additional representative images for Legacy Project, otherwise known as REL, aims to increase the legacy value of the ALMA Science Archive by reprocessing data from cycles 2 to 4, which will bring the reduction level of these data up to a level comparable to later cycles using the ALMA imaging pipeline. As REL continues, you will find more projects from earlier cycles that have been pipeline imaged that should be science-ready in the archive. For some specific cases, you can adjust the imaging pipeline calls within the script for PI to adjust the output of the imaging pipeline yourself. So if you would like to know more about image pipeline reprocessing, take a look at the CASA guides online. The remainder of the talk is going to focus on the process of manually imaging data products, but regardless of whether you would like to do image pipeline reprocessing or manual imaging, please note that the Allegro team is always happy to help. You've already seen this today, but to refresh your memory, this is the directory structure of your data. This is what you will get when you download your data from the archive and after you have applied the calibrations to your data. In particular, the calibrated directory will show up after you've applied calibrations, and this is where you'll find your calibrated measurement set. Projects that were not imaged through the pipeline will have a separate imaging script, and that will be located in the scripts directory where you find the script for PI. So if you do have a script for imaging script, that will be a good place to start when you are planning on doing your own manual imaging. And within the product directory, you're going to find cleaned images that were either produced through the imaging pipeline or manually through the QA2 process. Throughout the talk, I will be showing examples using the Science Verification Band 7 observations of the antennae galaxies of the CO3-2 line. Shown on this slide are the two mosaics of the antennae, divided into the northern mosaic on the left and the southern mosaic on the right. Today, I will mainly be working with the northern mosaic. In general, you want to work with the latest version of CASA to image your data. These are currently CASA 5.7 in Python 2 and CASA 6.1 in Python 3. The first step that you want to take in the imaging process is inspecting your data. Listobs and RMS are two very useful commands for doing that. Listobs will summarize the content of your measurement set, and RMS can be used to visually inspect your visibilities. But if you're looking for additional useful commands that can be used to inspect your data, you can check out the visibility information page located in the online CASA docs. After starting CASA, you can call the listobs command from the terminal, and it will output some basic information on your measurement set. If you only input your measurement set, it will output information into the logger, but you can also save this information to a file using the list file parameter. If you need to remind yourself of options for any command in CASA, you can do so in the terminal by using help. At the beginning of the listobs output, you will find general information on the observations of your data, including observation dates and times. You can also see the scan intent in the listobs output, and this may be useful if you are working with a measurement set that still has calibrator data in it. But what you will likely find most useful for imaging are the field and spectral window sections following the observation information. In the field section, you will see a list of all science fields in your measurement set and the central coordinates of their associated pointings. Each individual field is a unique pointing, so if a source has more than one field, then this observation is likely a mosaic. An exception to this are ephemeris observations of, for example, solar system objects. Following field information, you will see spectral window information, which will have spectral window ID numbers. In this example, we only have one spectral window, but most observations will have multiple. You will also find other useful information here, including the number of channels of each spectral window, the channel width, the total bandwidth, and the center frequency of your spectral windows. Besides this, there is also information on the antennas that were used in your observations and their locations, and you can find this at the bottom of your listobs output. After inspecting the basic information of your measurement set, you will want to inspect the visibilities. This can be done using RMS in CASA. If you put this command into CASA, this will bring up a GUI, and by default, RMS will show time on the x-axis and amplitude on the y-axis, and it will plot all of your data in your measurement set if you don't do any averaging. For imaging, you will likely want to plot the amplitude of your visibilities against channel, which is the example that I am showing here. If your measurement set has more than one spectral window with different frequency coverage, then you can either plot one spectral window at a time or choose to iterate over the spectral window axes. To iterate, you can set the iter-axis parameter to SPW and you'll be able to toggle between the different spectral windows in RMS. This is what the RMS GUI will look like. On the left-hand side of the GUI, there are a number of vertical tabs that you can use to adjust what you are plotting within the GUI. And just note that if you want to replot your data, that you should check reload before you hit plot. To save yourself some time, you may wish to average your data in RMS. And you can do this through the terminal as I've shown here, or you can do this within the RMS GUI. When you are averaging over time, you specify an interval in seconds, and this will average over the specified time within each individual scan. If you would like to average over all scans and therefore all time, then you need to set the average scan parameter to true. Keep in mind that as you average your data, you are removing information from these plots. You will want to select your averaging based on what information you are looking for from your visibilities. After inspecting your data, there are a few general imaging preparation steps that you can take, which are summarized here. This includes determining the channels with line emission that you want to avoid in the case that you are imaging continuum, or alternatively, finding the continuum-only channels for performing continuum subtraction. For any project, you will need to determine a cell size and an image size prior to imaging. One approach that you can take for adjusting these parameters is to produce a dirty image or cube. And this also gives you a direct way to estimate the RMS noise of your data prior to cleaning. Starting with continuum imaging, we will need to inspect the data to flag line channels. This is something that you can do manually in RMS, but the best way to do this is within the terminal. Here I'm showing you how you can manually select channels for flagging in the RMS GUI. In the center of the spectral window is the bright CO3-2 line, which we want to flag, and to the right of this we have an atmospheric line that should also be flagged. Once you select the visibilities, you can hit the red flag button to flag those channels out. Alternatively, you can do this more precisely in the terminal. To manually flag the channels with line data, you will be using the Flag Manager and Flag Data commands. The first step you should take is to save the flag version of your data before you do any flagging. We will restore this version of flags to the measurement set after we are finished making a continuum-only measurement set. After we save the original flag version, we will use the flag data command to manually flag out the channels that we know have line emission. And again, please note that Allegro staff are always happy to work with you or perform these steps for you. You can create a new measurement set that is dedicated to continuum using the split command. Since we are working with a measurement set that only has science targets in it, the calibrated visibilities will be in the data column. However, if you are working with a measurement set that still has calibrator data in it, the calibrated visibilities are actually in the corrected column. Finally, you can restore the pre-continuum flags to the original measurement set using the Flag Manager command. And you should always review your data in RMS after you've performed these tasks. This is what our flag data look like in the newly created continuum measurement set. We are only left with the visibilities in channels that were clear of line emission as we wanted. In the case that you have a project where the continuum is detected and you also have lines to image, you will want to perform continuum subtraction using the UV-consub command. This will produce another measurement set that has the input measurement set name with .consub appended to it. This measurement set will have the continuum subtracted spectral windows that you specify with the SBW parameter. The actual fitting of the continuum will be done on the continuum channels that you specify with the fit SBW parameter. After you've produced your continuum-only or your line-only measurement sets, you are generally ready to move on to making a dirty image. First, you need to determine the proper cell size for your image. And the suggested cell size is that which gives you 5 cells across the minor axis of your beam. Alternatively, if you want to nyquil-sample your beam, you would choose 2 cells across the minor axis of your beam. On this slide is an equation to estimate the cell size using your UV data. You need to input the longest baseline in units of wavelengths and the number of cells that you want across your beam. You can actually determine the longest baseline in RMS by setting the x-axis to UV wave, and this will plot the visibility amplitudes against the baseline length and wavelengths. Make sure you are not averaging by baseline or telescope here. This is what will pop up, and you can use this to visually determine the longest baseline. Now, I have pointed out the longest baseline here with the red arrow, and by plugging this value into our equation, I get a cell size of about 0.2 arcseconds. Next, you will need to estimate the extent of your image. If you have a single pointing, this is easy, and you can even estimate your field of view by calculating the half-power beam width of your primary beam. To be conservative, you should multiply this by some factor, like 1.5 or 2. Alternatively, if you have a mosaic, the easiest thing to do is to look at the extent of the products already imaged in the product directory, or to look at the mosaic pointing information in the weblog or QA2 report. In general, you want symmetrical shapes and round numbers, and CASA will tell you if it doesn't like what you're choosing. Another way that you can check the extent of your mosaic is using Analysis Utils. Analysis Utils is available for download as a Python package, and that can be imported into CASA. Here I am showing the results of the plot mosaic command in Analysis Utils, and I have chosen to use relative coordinates for determining the field of view extent. If you are interested in using Analysis Utils, more information can be found in the CASA guides. For imaging, you will want to select a weighting scheme, and the 3 main options are natural, uniform, or Briggs weighting. Natural will weight your visibilities according to the data weights. This tends to downweight longer baselines, since these baselines tend to have larger associated noise variance. This will give you a larger beam, but an overall lower RMS noise. Uniform weighting will instead weight the visibilities by their density in the UV plane. Because regions in the UV plane with higher UV coverage will be given more weight, this tends to reduce the side lobes of your data, but it can increase the RMS noise. Briggs weighting is a compromise between natural and uniform weighting, and the robust parameter adjusts the relative importance between uniform-like or natural-like weighting. The imaging pipeline will select that which provides the best compromise between noise and resolution. And this is typically a robust parameter of 0.5. Another useful thing that you can do with interferometric data is tapering. Tapering adjusts the UV weighting of our visibilities, which in turn will modify the size and shape of our beam. This is useful in the case that we want to reach a resolution comparable to that of another dataset. The only limiting factor is that we can only taper outer visibilities corresponding to the longest baselines, and this will degrade the resolution. We can instead choose to impose a hard cut to the inner visibilities. This is referred to as UV clipping, and I am showing an example here on this slide. So this demonstrates what happens to your UV visibilities when you set a hard cut, only allowing baselines greater than 50 kilolambda. So this is an important step to take when you are comparing against, for example, other interferometric data sets that have sensitivity to different scales. So we ideally want to clip our inner visibilities to match the minimum spacing of the comparison data. This is a comparison of the different weighting options that we have seen so far, plus a tapering example. In the left-hand column, we have natural weighting, and in the top panel, we have the point spread function, and in the bottom panel, we have an example image with the point spread function convolved to the signal. We can see that natural weighting results in the highest side lobes, but it will give us a lower RMS noise due to the increase in the beam size. Next to natural weighting, we have an example of the Briggs weighting with a robust parameter of 0.7. This produces a PSF with smaller side lobes than that of the natural weighting, and also a slightly smaller beam size. So the RMS noise will be a little bit higher in this image. And next to the Briggs example, we have uniform weighting, which has the lowest side lobes of the three weighting schemes that we're looking at on the left. And it will also have the highest RMS noise in addition to having the smallest beam. Next to this, we have the tapered uniform example. This, by far, has the largest beam size and the lowest side lobes. And this will also produce the image with the lowest RMS noise. After selecting the weighting scheme that we want, we can move on to creating a dirty map of our data using the tclean command. And we will start with a continuum example. We input the measurement set that we want to image from and specify a base name that will be prepended to all output images from tclean. These images include the main science image, which are the visibilities regridded into the image plane. We will also get the PSF, a residual map, a model, the primary beam, and a sum weight image, which will contain the peak of the PSF. If you are making a mosaic, you will also see a weight image. For imaging continuum, we will need to set spec mode equals to MFS, and this stands for multi-frequency synthesis. For a single pointing, we will want to set the gridder to standard, and this tells tclean that it only needs to regrid visibilities for one pointing. We also see a number of other input parameters here that we are already familiar with, including the image size and cell size. We also need to specify our field here, which can either be the field name or our ID number. And here I have chosen Briggs weighting with a robust parameter of 0.5. For creating a dirty map, we will want to set the number of iterations to 0, and we can set some arbitrary low RMS noise threshold for now. In this case, we don't need to work interactively with tclean, so we set interactive equals to false. Now if you let this run in our terminal, it will output a dirty continuum map with the additional images mentioned before. So this is the resulting dirty map of the commands that I just presented to you of the northern mosaic, but only imaging the center pointing, which is field 12. If we instead want to image the whole mosaic, the gridder must be set to mosaic, and we must specify the range of field numbers that we want to image. And we can find this range in the listobs output. When creating a dirty image of this mosaic, I am choosing a robust parameter of 2 to increase the sensitivity, since this is a science verification dataset taken with only 14 antennas. Additionally, we need to set a phase center. The phase center of the mosaic should be the field that is closest to the center of the mosaic setup. This will have already been chosen by the pipeline or during manual QA2 imaging. So again, you can refer to the weblog or QA2 report to find this. The phase center of the northern antennae mosaic is field number 12, as I've already mentioned. And you can also find this if you have analysis utils. You can use the plot mosaic command again, but this time by choosing do plot equals false. This might be useful if for some reason you have removed a pointing and need to determine the new center pointing. We can estimate the noise of our data from this dirty image either in the viewer or in the terminal using MStat. Since we want to exclude source emission when estimating the RMS noise, we should use a CASA region that avoids the source. It is easiest to create a CASA region within the viewer, but again, this can also be done in the terminal. CASA regions can then be input into the MStat command for calculating image statistics. To create a region in the CASA viewer, you can select a number of region shapes, and here I am demonstrating what you can do with a general polygonal region. When you have completed your region, you can then access the statistics directly in the viewer, which will include the RMS noise and Janskis per beam. You may wish to save this region to a file, which you can do under the File tab within the viewer. But make sure to save this to a CASA region file to ensure that it is compatible with the MStat command and other CASA commands. You may want to compare your noise estimate against a theoretical estimate using the radiometer formula or the ALMA sensitivity calculator. For example, if you've made adjustments to the robust parameter or the channel width or bandwidth, this will directly affect the RMS noise measurement that you get from your data. If you made modifications in calibration and flagged antennas, for example, then you will want to recheck this estimate. More information on this can be found in the ALMA Technical Handbook. At this stage, we are ready to move on to cleaning our dirty image. Cleaning is one approach to deconvolving the PSF of the telescope from your interferometric data and recovering the sky signal of your source. Cleaning in CASA is done with the tclean command through iterations of major and minor cycles, and deconvolution is occurring within the minor cycle in the image plane. The minor cycle receives the gridded residual image of your data with the model subtracted. It also receives the clean model itself and the PSF of the telescope. The minor cycle adjusts the model iteratively by searching for peaks in the residual image, subtracting the PSF from those peaks, and repeating this to adjust the model image. The model image itself is constructed with discrete components, which can either be treated as delta functions, which is, for example, used in Hogbaum or Clark cleaning, and is most appropriate for compact sources, or it can be treated on a multi-scale basis where components of different scales are linearly combined, and this is most appropriate for extended emission. The updated model is then subtracted from your data in the major cycle back in the UV plane on the ungridded data to produce a new residual image. These cycles are iterated until the stopping criteria are met. You can use the RMS noise to set the stopping criteria of the clean process. And in this example, I set 2 times the RMS noise as the stopping threshold. But you can adjust this based on your preferences or need. If auto-masking, you can specify thresholds in terms of signal-to-noise ratio, which we will discuss in a few slides. You can also set the maximum number of iterations, and here it is set to 10,000. In this example, we will be cleaning interactively and setting our own clean masks, so interactive is set to true. If you have a complicated source with multiple scales of emission, you may want to do multi-scale cleaning. However, this does not always improve your results, even in extended sources. I will use this as an example for the antennae data, and I do recover more flux with this method, but the difference is small. If you choose to do multi-scale cleaning on a dataset, you should also set the scales parameter according to the scales of emission that are present in your source. The scales should be input as a number of pixels, and it is recommended that you take multiples of your beam size. It is also recommended to include a 0-pixel scale, which corresponds to a point source. There are a number of additional parameters that you can adjust with multi-scale clean, and if you would like to know more about the different deconvolution algorithms built into tclean, you can find more information in the online CASA docs. When you enter this tclean command into CASA, it will bring up a GUI where you have the option to add or erase clean masks. The same shape tools are available for making masks that were available for making regions. If you are masking manually, you should only include emission that you are certain is real. To run only one major cycle of clean, you can hit the green circle arrow and you'll be able to continue adjusting the clean mask after it has completed the cycle. You will want to adjust the mask according to the residuals when the cycle is finished. For example, in some extended sources, you may find regions of emission that were not obvious in earlier cycles, and you may wish to add those to your clean masks. This particular dataset was not originally for continuum emission, and we only have one spectral window that we're working with, so the emission is very weak, and the source emission looks close to the residual emission even after one major cycle. You could hit stop here by hitting the red X, or you could allow clean to run to your stopping threshold by hitting the blue arrow. But in general, when you are cleaning your data, and if you're doing it interactively, you will want to clean until the source looks comparable to residuals, and then you will want to check the residual image after you are finished. And if necessary, you should continue cleaning. When imaging spectral lines, we will need to set spec mode equals cube. And we will also need to input the rest frequency of the line that we are imaging. To image an entire spectral window, you can set the number of channels equal to -1, and you can also set a starting value of channel 0 and a width of one channel. Start and width can also be specified in terms of frequency or velocity. If you would like all channels to have the same resolution, you can tell tclean to convolve all channels to a common beam by setting restoring beam equals common. tclean calculates the smallest common beam of all channels within your cube and uses that beam size. If you don't choose to restore your image with a common beam, each channel will have a slightly different beam size in your final image. To estimate the noise for a cube, you can still do so interactively in the viewer, but the statistics given are limited to the channel that you are working in. Alternatively, you can save a region in the viewer and then input this into ImStat to calculate statistics on only the channels that you are interested in imaging. This will return an RMS noise average across the channel range that you specify. Now, auto-masking makes the process of masking source emission and setting noise thresholds much easier since it estimates the clean masks for you. It allows you to set clean thresholds in terms of a signal-to-noise ratio, and auto-masking uses this to determine thresholds appropriate for each individual channel. In this example, I have set a number of auto-masking parameters that are useful if you plan on using auto-masking. First, to tell tclean to use auto-masking, set useMask equals to auto multi-thresh, or one of the other auto-masking options. tclean and auto-masking differentiates between side lobes and general noise, so we are able to set a threshold for both of these values. The side lobe threshold will be most relevant in the first few cycles of clean, and after this the noise threshold will become more important as side lobes are removed. Low noise threshold is the signal-to-noise limit that the initial masks are expanded out to. The min beam frac parameter sets the smallest area that a clean mask can have, and masks with areas smaller than this are pruned or removed. Row iteration sets the number of binary dilation iterations that tclean performs when it is expanding the clean mask out to your low noise threshold. Finally, I have also set the negative threshold here to a very high value because this dataset has prominent negative bulls due to missing short spacings, and we do not want tclean to mask these regions. If you have real absorption features in your data though, you will set this to a lower value. The GUI for cleaning cubes will appear very similar to that for continuum emission, except now we can move through the different channels of the cube. You are able to adjust masks using the options that are encircled on the slide. If you adjust a mask with all channels selected, it will apply that change to all existing masks within those channels, so some caution is required. Once you feel confident that auto masking is working the way that you want it to, you can hit the blue button to let it finish running without intervention. Once you have finished cleaning your data, you should perform a primary beam correction before doing science. This step can be done in CASA using the impvcore command directly on the CASA images. It also allows you to specify a cutoff and fraction of primary beam sensitivity for the output image. Here I have set the cutoff to 0.5, which will remove any regions where the primary beam sensitivity is below 50%. It is also common to do this correction on FITS files outside of CASA. You will likely want to convert your CASA images to a data format that is more widely compatible with other analysis tools, for example, the FITS format. You can do this using the export FITS command in CASA, and you can also specify the format of the spectral axis. Here I have specified that I want a velocity axis, and I want the optical velocity convention as opposed to radio. Additionally, you can choose to drop degenerate axes such as the Stokes axis if it isn't important for your data. At this point, you are ready to do science, or you can move on to self-calibration if you have a data set with emission that is bright enough.